Think of a computer like a busy kitchen, where the chef CPU is constantly chopping vegetables, running instructions. If a fire alarm rings, the chef must stop chopping and put out the fire before continuing. An interrupt works the same way. It is a signal that tells the CPU to pause what it is doing and deal with something more urgent. Without interrupts, the CPU would have to constantly check poll every possible event, which wastes time and energy. Interrupts let the system react quickly, just like the kitchen alarm, forces the chef to act instantly, making the whole process faster and more efficient. Interrupts come in 4 main flavors, each like a different type of doorbell. Maskable INT in 8085, IRQ in 8086. You can cover the doorbell with a cloth, disable it when you do not want the interruption. The CPU can decide to ignore it temporarily. Non-maskable RST 7.5, RST 6.5, RST 5.5 in 8085, NMI in 8086. This is a loud siren that cannot be covered. It must be answered immediately because it signals a critical problem. Software interrupt, RST instructions in 8085, INT3, INTN in 8086. The program itself can ring a bell by executing a special instruction, just like a child can press a button to call for help. Hardware interrupt, external devices such as keyboards or timers generate a signal on a pin. This is like a neighbor knocking on the door. Maskable interrupts can be turned on or off with the CPU's flag bits, while non-maskable ones ignore those flags and always get through. Explanation: when an interrupt happens, the CPU needs to know where to go to find the code that will handle it. This location is called an interrupt vector. Fixed vector: the address is hardwired. In the 8085, each RST instruction, RST0 to RST7, points to a fixed location. For example, RST0 points to address 0x000, and RST7 points to address 0x038. The 8086 has a fixed table for the first 256 interrupt types. Each entry is 4 bytes long, starting at address 0 in real mode. Dynamic or programmable vector: the CPU asks an external device for the address. In the 8085, the INTR line is dynamic. After the CPU acknowledges INTR, the device places its address on the data bus. For example, a peripheral sends address 0x020. The 8086 uses the interrupt descriptor table IDT, whose base address is stored in the IDTR register. Each entry can be changed by software, making the vector dynamic. Fixed vectors are like a mailbox that always sits at the same street number, while dynamic vectors are like a delivery service that tells you the exact apartment number each time. Explanation: not all interrupts are equal. The CPU must decide which one to handle first, just like a teacher decides which student's question to answer when several raise their hands. Priority in 8085. Hardwired order -RST 7.5 has the highest priority, then RST 6.5, RST 5.5, then INTR, then the maskable RSTS, RST 0 through RST 7. If 2 happen together, the higher priority line wins. Priority in 8086. The IDT entry number defines priority. Lower numbers have higher priority. The CPU also supports priority chaining, where an external interrupt controller, for example Intel 8259A, can cascade multiple controllers, creating a tree of priorities. The controller sends a priority encoded request to the CPU, similar to a line manager passing the most urgent request upward. Cascading means you can have many devices, like dozens of students, but only a few hand raisers, controllers, that tell the CPU which group has the most important request. An interrupt service routine, abbreviated ISR, is a short program that runs when an interrupt occurs. Its structure can be thought of as a 5-step recipe. Step 1: save context. Store registers that the interrupt service routine will use. For example, push program counter, flags, general purpose registers, so the original program can continue later. In 8085, you typically push the accumulator and flags. In 8086, you use push-a-D or individual push instructions. Step 2: acknowledge the interrupt. For INTR, the CPU executes EI and then the device places its vector. The 8086 sends an interrupt acknowledge cycle, abbreviated a EN, to the controller. Step 3: execute service code. Perform the needed action, read a key, clear a timer, and so on. This part should be as quick as possible. Step 4: restore context. pop the saved registers back to their original values. Step 5. Return from interrupt. Use RET in 8085 or IRET in 8086, which also restores the status flags and program counter. Timing: each push or pop and return instruction takes a known number of clock cycles. For example, push in 8086 equals 3 cycles, IRET equals 4 cycles. The total interrupt service routine time equals the sum of these plus the time of the actual service code. Think of it like a quick pause in a game. You save your current score, deal with the pop-up, then restore your score and keep playing. Interrupt latency is the delay between the external event and the moment the CPU actually starts executing the ISR. It can be broken down as latency equals T sub ACK plus T sub vector fetch plus T sub pipeline flush. For 8085, after INTR is asserted, the CPU finishes the current instruction, then performs an interrupt acknowledge 2T states. The peripheral then supplies the opcode, for example RST7. So L sub 8085 equals T sub current inster plus 2T plus 1T sub opcode fetch. For 8086 running at a clock period T sub CLK, the latency in nanoseconds is L sub 8086 equals N sub cycles until next instruction boundary times T sub CLK plus 2 times T sub CLK plus 4 times T sub CLK, where the extra 4 cycles are the interrupt acknowledge bus cycle. Response time equals latency plus ISR execution time plus return overhead. If the ISR needs N sub ins instructions and each takes C sub I cycles, then RT equals L plus sum from I equals 1 to N sub ins of C sub I plus C sub return. These formulas let designers estimate whether an interrupt will be fast enough for real-time tasks like motor control. For example, with a 5 MHz 8085 clock, T equals 200 nanoseconds. A simple ISR of 10 cycles takes 2 microseconds, plus about 1 microsecond latency, total about 3 microseconds response. Explanation: to make a noisy real-world signal usable by the CPU, you need hardware interfacing. Signal conditioning: convert the voltage level of the external device to the microprocessor's logic levels, for example 0 to 5 volts for 8085 or 8086. This often uses resistors, diodes, or opto-isolators to protect the CPU. Edge-triggered versus level-triggered. Edge-triggered reacts to a sudden change rising or falling. Edge is like a clap detector that only cares when you clap, not how long you keep your hand up. Level-triggered stays active as long as the signal stays high or low. It is like a light switch that keeps the light on while you hold the switch down. The CPU will keep acknowledging the interrupt until the level goes low again. Debouncing: mechanical switches bounce a small RC filter or a flip-flop, cleans the signal so the CPU does not see multiple interrupts for a single press. Interrupt lines: each line, INT, RST 7.5 etc. must be tied to the appropriate pin on the peripheral or controller with proper pull-up or pull-down resistors to guarantee a defined idle state. These steps ensure the CPU receives a clean, well-timed interrupt request, just as a telephone line needs a clear ring before you answer. The CPU provides several software instructions to control interrupts. Enable EI8085 or STI8086 sets the interrupt enable flag, allowing maskable interrupts. Think of it as turning the listen switch on. Disable DI8085 or CLI8086 clears the flag, ignoring maskable interrupts, like putting the earplugs on. Acknowledge: when enter is asserted, the CPU executes an interrupt acknowledge cycle where the device places its vector on the data bus. In 8085, this is automatic. In 8086, the INT, a line of the 8259, is used. Mask bits: in 8085, the SIM instruction set interrupt mask can individually mask RST 5.5, RST 6.5, and RST 7.5. In 8086, the IF flag in the flags register controls all maskable hardware interrupts, while the IOPL field can restrict changes to privileged code. Priority change: on the 8259, you can program the priority order by writing to its command registers. The 8086 can also change the IDT entry addresses to redirect vectors. Using these commands, a program can temporarily turn off interrupts while it updates critical data, then turn them back on ensuring data integrity, much like pausing a game while you save your progress. Overall, the software control works hand in hand with the hardware to give the programmer full authority over when and how the CPU will answer external requests.